The first theorem which shows the equivalence of pushdown automata and context-free language. The theorem statement is every context-free language is recognized by some pushdown automata. So that means CFL we already know. CFL is type 2 language. Then PDA is type 2 acceptor. That means CFL is accepted by only its acceptor, that is PDA. Then reversely, PDA accepts only type 2 language, that is context-free language. Then wherever context-free language is there, so that is described by its grammar, which is called as context-free grammar. So now here you can see equivalence of PDS and CFLs by considering context-free grammar. Now the statement is a PDA-M can be constructed to accept the sentences generated by context-free grammar. So here we have to construct or obtain a PDA which accepts the sentences which are generated by its grammar, that is context-free grammar. So this is the equivalence theorem. So according to this theorem, here we have two conversions. First, for a given context-free grammar, we can obtain its equivalent pushdown automata. Then second one, for any given pushdown automata, we can construct its equivalent context-free grammar. Here two conversions are there. So in this lecture, we will discuss the first conversion, that is context-free grammar to pushdown automata. Now let us see. There are some steps we have to follow. So whenever if you want to accept a context-free grammar by pushdown automata. So as part of equivalence of PDAs and CFLs. So now we have a PDA. Now a context-free grammar is given. Now from the context-free grammar, derive any string which can be derived from the given context-free grammar. Then we have to verify whether the string is accepted or not by the given PDA. For that, the following steps are applied to accept a context-free grammar by a pushdown automata. So before reading any symbols from the input, that means from the input tape, put an end of stack marker, and the start symbol into the stack. So here initially the stack contains Z0, which is called as the initial or start symbol of the stack. Before reading input, stack contains Z0, means contains only start or initial symbol, which is also called as end of stack marker. Then if there is a variable A on top of the stack, so then next step, if there is a variable on top of the stack, let us say capital A is the variable. That variable is also called as non-terminal. So then replace it by a string in P of A, where P is nothing but productions. Suppose we have the productions. Suppose A derives alpha is a production of A. Now initially stack contains initial symbol Z0. Then second step, if stack pop contains a variable A. Now this variable A is replaced by its productions, that is right hand side value. Now this will becomes Z0. Now A is replaced by alpha. Now stack pop contains now alpha value. Now see, that is the second step. So now next step, what you have to do, if there is a terminal on top of the stack, if alpha is a terminal, single terminal value, then you have to perform pop operation. Then you have to read the next input symbol and compare the two. That means the next input symbol on top of the stack. So if the input symbol on top of the stack both are same, if they match, go on, continue to next step. Suppose if input symbol on top of the stack are not same, then reject. So finally, you can repeat this process. Finally, if the end of stack symbol is on top of the stack, that means only now Z0 will be there on top of the stack. So then you can say accept. Finally, the string is accepted by the PDA. Then the string is derived from the context free grammar. Therefore, context free grammar is also accepted. These are the steps you have to follow. Anyway, during solving the problem, we will demonstrate the acceptance case also. Now let us come to the procedure for converting a context free grammar to pushdown automata, the first conversion. So CFG to pushdown automata. So let us take a context free grammar G equal to VTSP is the given context free grammar. From this grammar, we have to obtain a PDA M with 7 tuples Q, sigma, tau, delta, Q naught, Z naught, F. Now, how to obtain or how to construct a PDA for a given context free grammar? So as per the following steps, so we have to apply for constructing a PDF for a given context free grammar. So the steps to be followed to convert a context free grammar to its equivalent PDA are shown below. So these steps now we will call it as rules. So by using the following rules. So according to rule 1, this rule 1 we can apply for each and every variable in the given grammar. That variable also called as non-terminal. So for each variable or non-terminal, include or add the following transition. Here you can see the transition delta of, we can take one state Q with empty input as null, then stack. So this is nothing but stack. Now next state, then after the move, what stack contains. So now you can see stack before and after the move. So here you can see before it contains A, the variable A, after it contains alpha. So what are these A and alpha? These are nothing but where the production rule is of the form. So in the given context free grammar, if your production is in this form, A derives alpha. So this A is placed in the left hand side of the move in stack, then alpha is placed in the right hand side of the move, so on the stack. So whatever the variable A that will be placed in the left hand side of the move on the stack. Then whatever the value of alpha, here alpha is a string of variable or terminals. So that complete value can be placed onto the stack in the right hand side of the move. So for all variables, you can apply rule 1 by seeing the productions in the given context free grammar. Then according to rule 2, so this rule can be applied for terminal symbols. So for each terminal symbol, add the following transition. Irrespective of the productions, you can find what are the terminals in the given grammar. For each and every terminal, add the following transition. So the transition is like this, delta of Q, same state. So here A is the input symbol, then stack top is also contains A. So this A is nothing but terminal symbol. You can take input and stack top, both will be the same terminal symbol. So then delta of Q A equal to Q comma null. That means here you are erasing the stack symbol, that is pop A for every terminal symbol A. For example, let us take T equal to A comma B. So in the given grammar, terminals are A, B. So for each and every terminal, you can apply this rule too. So the first one same as it is this one. So that is a delta of Q comma A equal to Q comma null. For every terminal, you can take input and stack top will be the same terminal. Then the second one, the second terminal is now B. Now same state Q, input is B, stack top is also B. Then simply you have to pop. So irrespective of productions, Here we are not seeing the productions. Simply in the given grammar definition, whatever the values of P for each and every value, you can apply rule 2. That means for every terminal input and stack top, we have to take the same terminal value. So for A, you can apply this one, QAA. For B, QBB. Suppose another terminal C is also there. The third transition is delta of Q comma C comma C. So like that, input and stack top should be same. So then for every variable, you can apply rule 1. Then for every terminal, you can apply rule 2. So by applying rule 1 and rule 2, now we can obtain all the transitions. Once transitions are obtained, then you can write the tuple values of PDA as per the definition. PDA m equal to Q sigma tau delta Q naught Z naught F. So now we will solve one problem. Then here you will get clear idea. So the question will be given like this. Here see one of the question taken. So construct PDA for the given context free grammar. So now here you can observe context free grammar is given in the form of productions. So S derives 0 BB, B derives 0S or 1S or 0. Then also you have to test whether the string 0, 1, 0 power 4 is accepted or not. So in the entire of formal language and automata theory course, the strings can't be represented with powers. So you have to expand wherever powers are there. So now 0, 1, 0 power 4 is nothing but 0, 1. Expand 0 4 times. 0, 0, 0, 0. Actually, this is the string. So this string you need to check whether it is accepted by the constructed PDA or not. So first we have to construct the PDA. Finally, we will check whether the string is accepted or not after constructing the PDA. So now what you have to do first, write down the given context free grammar G equal to P comma T comma S comma P. Write down all the tuple values where variables capital V equal to what are the variables in the given grammar. In the productions you can see the first production left hand side it contains S, then the second production left hand side it contains B. So SB are the variables. Even right hand side also you can see if any other new variables are there. So the first production S derives 0 BB, right hand side it consists of B's only. Then B productions right hand side it consists of S only. So SB already repeated. So therefore you can take only unique variables. Now V equal to S comma B. Now terminals T equal to, in the given grammar production, see the lowercase letters or lowercase letters or digits or any operators or any symbols, all you can consider as terminals. Now in the first production S derives 0 BB. So 0 is the digit, so which is called as a terminal. Then the second production B contains 0S, 0 already repeated. Then 1S, so 1 is another one. Then again 0, this already repeated. You can take only unique terminal. So terminals are 0, 1. Now S is the starting variable which can be taken from V. So already in V S is there, but check out whether S is starting variable or not. How to identify? In any given grammar, the first production. In the first production, left hand side variable, whatever the variable, that is nothing but starting variable by default. Now in the given grammar, S derives 0 BB in the first production. So by default, left hand side S is there. So therefore, S is belongs to V, is start variable of the grammar. Now other missing tuple is P. Now productions already given in the question itself, so you can take as it is. So here we have two productions. So one is starting with S. So S derives 0 BB. Then second production starting with B. B derives 0S or 1S or 0. Here you can see B consisting of three productions. So all three are combined starting with the same left hand side variable. So here this is nothing but B derives 0s is one production, then B derives 1s is another production, then B derives 0. So here it has three productions. So all these three productions starting with the same variable B. That's why all three are combined by using R symbol. Now these are all the productions. So now we have to construct the equivalent PDA for the given context-free grammar. Construction of PDA. So we have to apply as per the procedure. There are two rules. So by applying rule 1 and rule 2, so we can find the equivalent transitions based on the productions. So first apply rule 1 for all the variables in context-free grammar. So here variables are v equal to s and b. So for the variable s and b, you can apply rule 1. Now write down the s productions. First, s derives 0 bb. So then by rule 1, see the following transition is obtained. So delta of a state q with empty input. So now here you can see equal to, again next state is also same. Here you can see. So here our general form of the rule is A derives alpha. So this A you can place here. Then this alpha you can place here. Now in the given grammar, left hand side is nothing but A. The right hand side entire value is nothing but alpha. Now you can substitute these values. Delta of q comma epsilon comma. Here A is S equal to q comma alpha equal to 0 bb. Now this is the transition corresponding to the production S derives 0 bb. So then similarly take B productions. So B consisting of, here we have three productions. So all three separately you can apply. B derives 0s or 1s or 0. So here three productions are there. Three times we have to apply rule 1. Now B derives 0s, then B derives 1s, then B derives 0. So by rule 1, here you can see, let us assume this is A, this center one is alpha. Then this is again A, this center one is alpha. Here again this is A, this right hand side is alpha. So now by rule 1, we can apply rule 1 for all these three productions of B. Now the first one, here you will get delta of q comma empty string, that is epsilon comma. Here you can take A equal to q comma. Here you can take alpha. So now here A means this one. This B value comes here. Then right hand side alpha value comes here. Now this is B. Now this is 0 s. Then similarly B derives 1s. Here you will get delta of q comma epsilon comma B equal to q comma 1s. Then similarly for last one, delta of q comma epsilon comma B equal to q comma 0. Here alpha is 0. So simply we have substituted A and alpha values in the transitions. Therefore, finally, the remaining transitions, what we obtained here, the second transition is this one. Delta of q comma epsilon comma B equal to q comma 0 s. Then the third transition, delta of q comma epsilon comma B equal to q comma 1s. The fourth transition, delta of q comma epsilon comma B equal to q comma 0. Here you can observe one similarity for these three transitions. Left hand side you can observe. So same state, same empty input, same stack symbol. All the three transitions, left hand side contains same state, same input, same stack symbol. But right hand side consisting of different values. So these three can be combined like this. So delta of q comma epsilon comma b equal to, here we have three next moves. All you can include in brackets. The first one is q comma 0s, second one is q comma 1s, the third one is q comma 0. So now this entire transition will consider it as the single transition. So delta of q comma epsilon comma b. Then by applying rule 2. Now rule 1 is applied for all the variables. We have only two variables s and b. So we applied rule 1. Then by applying rule 2 for each terminal, symbol. Now you can see according to rule 2, here in the given grammar, what are the terminals here? We already written t equal to 0 comma 1. So now the first one for the terminal 0, q input is 0, stack top is also 0, then q comma null. So here we have to pop 0 from the stack. Then second terminal is 1, delta of q comma input is 1, stack top is also 1. Now q comma epsilon. Now here pop 1. So these are all the two more transitions obtained by using rule 2. Then you can make it as the number. Now this is the first transition. Now this you can make it as second transition. Now this you can make it as third transition. This you can make it as fourth transition. Therefore, final PDA. Now you can write on the final PDA m equal to q sigma delta q naught, here tau is also add, z naught f, where now list all the tuples, where q equal to, from the above transitions, what are the states we used? We used only one state. Then sigma equal to, what are the input symbols here? 0, 1. Then how to find tau value? Tau is nothing but v union sigma. So now what are the variables in the given grammar? S and b. Then what is sigma? Here what we obtain? 0 comma 1. So now here what is the z naught value? Z naught value can be obtained based on the starting variable. So in the given grammar, s is the starting variable. Now this will be treated as z naught. So therefore here z naught equal to s. That is the initial symbol of the stack. Then q naught equal to q. Here we have only one state we considered. So that is initial or start state. Then z naught equal to s is the stack initial symbol. Now final state. Here only one state we have considered. Then consider same state as final state also. Is final or accepting state. Now delta we already obtained above. Again you can write down all the transitions, and delta is shown below. Now write down all the transitions here. The first one is delta of q comma epsilon comma s equal to q comma. So what is the first transition? So q epsilon s equal to q comma 0 bb. 0 bb. Now the second transition, delta of q comma epsilon comma b. Here we have three next moves. First one is q comma, what are the values here? So 0s, 1s and 0. The first one is 0s, the second one is 1s, then third one is 0. The third one is 0. Next, third and fourth transitions with the terminal combinations. Delta of q comma 0 comma 0 equal to q comma null. The fourth one, delta of q comma 1 equal to q comma null. So now this is the final PDA. So now we have to draw its transition diagram also. Transition diagram of PDA obtained here. So here we have only one state, that is Q. Initial state also same, final state also same. Then this is initial and final state. Now all the transitions going to same state itself, that is loop. Here you can write down all. First one is with empty input. Here you can see the stack contains S followed by 0 BB. That is the first transition. Then second transition, empty input, the variable is B followed by 0s. Then again same, B followed by 1s. Then again same, B followed by 0. So this is the second transition, 3 next moves going to same state. Then third and fourth. So your input is 0. Stack also contains 0, that is replaced by null, that is pop. Then 1 by null. Now see, all transitions are included here. So now this is the transition diagram. Now you can verify acceptance. To accept the string in the given problem, the string is 0 1 0 power 4. This is nothing but 0 1 0 0 0 0. So now how to verify the acceptance? So the acceptance condition is same what we discussed in our previous lectures. First you can take the initial state Q, comma the complete string you can take 0 1 0 0 0 0, then stack initial symbol. But here z not equal to yes. Here the initial symbol of the stack is yes. That you can substitute Q 0 1 0 0 0 0 yes. Now initially beginning of this lecture we discussed some points, various steps which are used to verify a context-free grammar whether that is accepted by PDA or not. So before input, then you can place an empty symbol on the stack, that is Z0. Here Z0 is nothing but yes. So now stack contains initial symbol or end marker of the stack. Then if stack top contains a variable or non-terminal, what you have to do, you can substitute its equivalent productions. Now stack top contains here yes. Yes is the variable. Now you can substitute yes by its equivalent productions. So now you can recall the productions here. S derives 0 BB. So now S is replaced with 0 BB. Now you can list all the productions here. S derives 0 BB. Then B derives 0s or 1s or 0. So this we will use here. Wherever stack top contains a variable, you can substitute the corresponding productions. Now you can see here S is there. S is replaced with 0 BB. Now this will becomes Q comma. Input, there is no change in input. The input remains same. Now S is replaced with 0 BB. Here you can write and comment what you did. S is replaced with 0 BB. So now here you can see the next step. If input contains a terminal, anyway input contains only terminals, then stack top contains a terminal and input is same as the stack top, then what you have to do, we have to pop. We have the transition delta of q comma 0 comma 0. So here you have to pop 0. Now the remaining input is 1 0 0 0 0. Now the remaining symbols on stack are bb. Now you can see again top of the stack contains a variable or non-terminal. So we have to substitute this by its productions till we will get a terminal on top of the stack. Now B consisting of 3 productions. Now which production is useful here? If you can substitute 0s, then 0s, then the top is 0, but input is 1. So both are not matching, here reject. So then another one, if you can substitute 1s, if you can substitute B as 1s, now stack top is 1, input is 1, now matching. So you can pop 1. So the second substitution is suitable here. Now q comma 1 0 0 0 0. Now this b is replaced with 1s. This b remains same. Here what we substituted. So b derives 1s. Now input is 1, stack top is 1. Then you have to pop. Then you will get q comma. The remaining input 0 0 0 0. 1 is popped. The remaining symbols are sb. Now again you can see stack top contains s. Yes, we have only one substitution. So directly you can substitute that. Now q comma 0 0 0 0 s equal to now 0 bb. Already one b is there. So now here what we substituted, s derives 0 bb. Now you can see stack top is 0, input also 0. Then you have to pop. Now q comma 0 0 0. Now the 3 b's remain same. Now you can see stack top contains a variable or non-terminal. So this you have to substitute by its terminal. Here which value you need to substitute for B? Here you can see B contains single terminal 0. Here input also we have 0. So you can substitute 0 only. Now B equal to 0. Now remaining B is as it is. Now here what we substituted, B derives 0. Now see input is 0, stack top is 0, both are same. We have to pop, both are terminals also. Now q comma 0 0 comma, now the remaining variables are on stack. Now here again stack top contains a variable b. Now you can substitute. Now input is 0, b again you need to substitute only b. So now here b derives 0 is substituted. Now input and stack top both are terminals and both are same. So you have to pop now q comma 0 comma b. So now finally again stack contains a variable. Replace it by its terminals q comma 0 comma. Now which one you need to substitute? Input contains only single 0. So b also you can substitute single 0 because you have a single terminal 0 for b. Now you can see again input is 0, stack top is 0. Both are terminals and matching. So you have to pop q comma. Now input is empty. Now after deleting 0 from stack, then what stack contains? Yes, that is the initial symbol q comma epsilon comma z naught. Now here you can see input is empty. Stack also contains initial symbol. So then if here q is a final state, if you can consider q as the final state, anyway here we already assumed q as the final state. Therefore the string, a given string 0 1 0 0 0 0 is accepted by the PDA with the final state. With the final state combination, this string is accepted. Suppose if you don't have a final state, see the last step here you can rewrite like this. So this you can take as it is q comma epsilon comma z naught. Then this will be written as q comma epsilon comma epsilon. Here you can see stack is null. Stack is null and q is not belongs to final state. So in this case, the string 0 1 0 0 0 0 is accepted by the PDA with null stack, null or empty stack. So these cases we already discussed during the acceptance of languages by PDA. So we have the possible cases with the final state, then with empty or null stack, then with both combinations. So then the third combination, suppose here q comma epsilon, here q belongs to f, then stack is null. Now in this case, the third combination, the string 010000 is accepted by the PDA with both the final state and empty stack or null stack. Empty or null stack. These are all the three cases of acceptance of a string or language by a PDA. Now see, whatever the PDA we constructed here for the given context-free grammar. So whatever the PDA we obtained, now the given string 010000 is accepting with the PDA obtained here. So by all the cases, by the final state, by empty or null stack, by both the final state and empty or null stack combination. So this is the final solution of this problem.